Hello. Today's video is for the Administration Computer-Based MIS class for Professor Carl Scott. My name is Vicki Lee, and I am representing Team 12, which includes Michael Coffey and David Franco. Today, we will be going over Moore's Law, and we will be delving into how it relates to power consumption. Moore's Law. What is it? It is an observation that over the history of computing power, the number of transistors on an integrated circuit doubles approximately every 2 years. An example of this is to your right. Moore's Law for power consumption is a power consumption of nodes doubling every 18 months. Now first off, who is Gordon Moore? Moore is the co-founder of Intel, who observed an alarming trend. The number of components per chip was roughly doubling every year, which reached to about 64 components in 1965. Moore predicted that chips with 65,000 components will be available by 1975. Moore's observation of exponential growth has proven to be one of the greatest examples of pre-science in the modern age. Another question to be raised: is power consumption a problem? A prime example is as computing muscle increases over time, gadgets such as smartphones require less energy per computation, although they require more charging. Elaborating off of this, the double of computing power per 18 months has made it possible for most organizations and corporations to use information systems for their core production processes. As stated in the article of Moore's Law for Computers and Energy Efficiency article, which is cited at the end, states that researchers found that over time, computers do more work per energy input, but the number of computations per kilowatt an hour doubles. And there's a long-term improvement in computational efficiency because battery technologies have not improved in the past nearly as rapidly as semiconductor technology. In the early 2000s, power consumption was seen as a very critical situation. That the supercomputers were not as efficient in the use of space that they occupied. What would often result is the design and construction of new machine rooms, and in some cases, entirely new buildings were built for the sake of containing these supercomputers. As to why they required so much space was not that only do these supercomputers consume power, but they must also be spaced in order to be aggressively cooled down. Stemming from that, recently, according to Professor Kumi, who is a consulting professor in the Department of Civil and Environmental Engineering at Stanford University, has stated that the energy efficiency of computers will roughly double every 18 months. What contributes to this theory is that the power improvement has reduced component size, capacity, communication time, and an increase in energy efficiency. As stated in a recent interview, Kumi said, "Doubling every year and a half means that over the course of 10 years, the efficiency of computers will go up by a factor of 100. That means we will be having the ability to have more and more mobile centers that use less and less power to collect information and also to bring it back to some wireless base station. The people who are doing the most interesting work now are focused on an ultra-low power computing that was never before possible." Kumi's observation and research has came to be known as Kumi's law, and possibly an improvement on Moore's law. So what does this mean? What happens to Moore's law in the future? Many theorize that there will be a physical limit to transistors, and that in the next 10 years, we are approaching the end to the method for scaling transistors. And there are many who believe that Moore's law is already collapsed. According to theoretical physicist Michio Kaku, there is an ultimate limit set by the laws of thermodynamics and set by the laws of quantum mechanics as to how much computing power you can do with silicon, says Kaku. Also noting that the reason why the age of silicon will eventually come to a close. And he even goes on to say, sooner or later, even three-dimensional chips, even parallel processing, will be exhausted, and we have to go to the post-silicon era. So what does this mean for us users in the end? These new findings have a great implication for future computers and batteries. Theoretically, we are very far from the limit of how much power and electricity we can save. It was projected in 1985 that we could improve energy efficiency by a power of 100 billion, but we have only hit a factor of about 40,000. But this observation and increase in energy efficiency provides a very bright future for computers and battery-powered gadgets. In the future, according to Professor Kumi, there is hope for computers and gadgets. Low power that doesn't require external electricity in the form of a battery or some other sources opens up all sorts of possibilities. In this day and age, we have become more reliant upon our devices and need the increased performance of power in computers and mobile phones. It will also expand our capabilities in how we obtain and analyze data, and how we use the data to make decisions. We will be enabled to control certain business processes with more knowledge, precision, and interact with data in real time. Lastly, here's our citation for where we received our information and references. Thank you very much for listening.